Hi everyone. So now I am going to present my project Real-time lane detection and steering angle calculation for autonomous cars. As many of the latest technologists have predicted, self-driving autonomous cars are going to be the future in the transportation sector, and many of the billion-dollar companies like Google, Uber, Apple, etc. have already started working to come up with the safest way of making a road vehicle completely autonomous. So lane detection plays a major role in this, and I have tried to do one of the important part of it, which is detecting the steering angle of the car from a real-time video input. The main idea is to use the embedded systems to develop a day-to-day use system, which is an improvement to an existing system. That is, to automate a difficult task using embedded systems. So the main goal is to make a vehicle run in road without any human intervention, and detection of steering angle is the most important part of it. So I have mainly developed two systems. System 1 represents the detection of lane lines from a pre-captured video input using the algorithm of canny edge detection and huff transform coded in OpenCV Python. This system gives us a video output with lane lines highlighted in it. System 2 represents the detection of steering angle output. This steering angle is the one which provides information to the autonomous car about the angle with which it should turn. So in this system, I have used a Raspberry Pi camera connected to the Raspberry Pi Model 3. The Pi camera captures the real-time video of the lane lines present right in front of it, processes the image to find the lane lines, and finally calculates the angle of those lines with the horizontal and outputs it. The main hardware requirements are Raspberry Pi Model 3 and Raspberry Pi Camera version 2.1 for the detection of steering angle and lane lines. And the HDMI cable and monitor are needed for coding, compiling, and demonstrating the results. The software configurations used are OpenCV Python and C++. The main reason I selected Raspberry Pi Model 3 is that it has the provisions for networking. It has an Ethernet as well as 2.4 GHz Wi-Fi through which I could install OpenCV in it. Another important point for choosing that is it has a very user-friendly camera serial interface through which real-time video processing becomes less complex. It also has a 4 USB ports through which we can connect the mouse, keyboard, etc. and a HDMI port through which we can connect a monitor. This helps in installing the software, coding, compiling, and running the program. PyCamera version 3 has an average 8 megapixel camera resolution, and it also captures video at high resolutions. It has improved white balance and image quality. Almost all software is supported within the latest version of Raspbian OS. I have selected OpenCV, which is open source computer vision for the software, as it is the most popular library in computer vision. It is a library of programming functions mainly aimed at real-time computer vision, and it is mainly used for the purposes related to processing of images. It has different flavors in C, C++, Python, and even Java interfaces, out of which Python or C++ version were more user-friendly for me. It supports Windows, Linux, Mac OS or iOS, and Android as well. It is designed for computational efficiency with a strong focus on real-time applications. Written in optimized C or C++, the library can take advantage of multi-core processing also. It also offers optimized implementations for more than 2,500 algorithms. So let's see our first system. So this is the input video which I took for processing and outputting the video with highlighted lane lines. This input video is of 10 seconds duration. I have also tried with another video input which is of more time duration and got the same results as of this. So now let's see what is the algorithm for lane detection. The step 1 is the noise removal. Usually it is recommended to denoise the image or remove the noise from an image before starting the process. For that, we convert the RGB image to grayscale and blur it for better accuracy. Step 2 is the canny edge detection. The edge detection technique used here is canny edge detection. The name refers to John F. Canny, who found this algorithm in 1986. In this technique, the goal is to find the boundaries of an image in an object. To do that, we compute the gradient of the image with the brightness of each pixel corresponds to the strength of the gradient at that point. We can find the edges by tracing out the pixels with the strongest gradient. Next step is to focus on just the region of interest of the image that interests us, namely the region where the lane lines are. In this case, I'll assume that the front-facing camera that took the image is mounted in a fixed position on the car such that the lane lines will always appear in the same general region of the image. For this purpose, you can see that I'm using the four variables which represents the vertices of a trapezoidal region that I would like to consider for my lane detection algorithm, and it is highlighted in the picture. The final step is to apply the Huff transform. It is a feature extraction technique used in image analysis, computer vision, and digital image processing. The classical Huff transform is concerned with the identification of lines in the image. Here in the image, a line is spotted as X versus Y, but in 1962, Paul Huff devised a method for representing lines in parameter space, which we call Huff space in his honor. In Huff space, I can represent my X versus Y line as a point in M versus B instead. So the Huff transform is just the conversion from image space to Huff space. So now I am going to show the live demo for highlighting the lane lines detection with the video. So for this, I have used the OpenCV Python installed in a Linux machine. So here is the code of mine, and I'm going to run this. So I got the output video here. So you can see that the video has the lane lines highlighted in it, but still we can see that the video is running too slowly because I'm using the virtual box inside the virtual box of Linux inside the Windows. So I have downloaded this video output from the file manager and emailed to my account, and I downloaded it in my Windows machine, and I have put that output video in the presentation here. So you can see that this video is more smoother. So here we can see that the lane lines are highlighted in the video in every frame of the image. So let's see our next system, which is the real-time steering angle detection on video input. So this steering angle is the angle of the lane lines with the horizontal, which gives us information about with what angle should the autonomous car turn. So for calculating the steering angle, first of all, the lane lines are identified from the real-time video input captured by the camera using the algorithm explained now, and then calculates the angle of these lines with the horizontal. So there are three steps in the algorithm, and the first step is the geometric camera calibration, which is also referred to as camera resectioning, which estimates the parameters of a lens and image sensor of an image or video camera. You can use these parameters to correct for lens distortion, measure the size of an object in world units, or determine the location of the camera in the scene. So these tasks are used in applications such as machine vision to detect and measure objects. They are also used in robotics for navigation systems, 3D scene reconstruction, etc. And the next step is to find the lane lines from the real-time video input. The algorithm is the same as that of system 1. So converting the color image to grayscale, blur it, use canny edge detection and Huff transform to find the lanes. And the step 3 is to find the steering angle of the lane lines from the real-time input. So the logic for that can be summarized as whenever a new image is found by the Pi camera, find the lane lines in it, and if there is a line crossing our path of view, we print the steering angle as the output. Otherwise, we assume that the lane lines are straight and thus the steering angle is set as 0. This angle output is represented relatively from minus zero point 0.5 to zero point 0.5, where 0 indicates the straight line. As part of the performance measurement in this project, first of all, I did the camera calibration and estimated the parameters of the Pi camera. These can be used to correct for lens distortion, thereby helps in finding the lane lines and its angle accurately. Then I could also find the FPS or frames per second, which is a measurement for how many unique consecutive images a camera can handle each second. It is given by the number of total frames captured divided by the total runtime duration. So ideally, this FPS should be high, and as FPS increases, precision or accuracy of the output increases. I got an approximate value of 30 frames per second, which is a good value.